will be discussing the problem valid binary search tree. The problem statement says given the root of a binary tree, determine if it is a valid binary search tree BST. Given the root of a binary tree, a valid BST is defined as follows. The left subtree of a node contains only nodes with keys strictly less than the node's key. The right subtree of a node contains only nodes with keys strictly greater than the node's key. Both the left and right subtrees must also be binary search trees. The problem asks to check whether a given binary tree satisfies the global rules of a BST, not just local parent-child comparisons. In a valid BST, every node's left subtree must contain only values strictly smaller than the node, and every node's right subtree must contain only values strictly larger, and this constraint must hold recursively for all subtrees. This means a node deep in the right subtree must still be greater than all its ancestors, not just its direct parent. For example, 2, 1, 3 is valid because all left values are smaller and all right values are larger. But 5, 1, 4 null, 3, 6 is invalid because value 4 appears in the right subtree of 5 being smaller than it, violating the BST ordering. The core idea is to ensure each node's values stays within a valid range defined by its ancestors, which is why simple child only checks are not sufficient. The solution code enforces value boundaries as it traverses the tree recursively. The helper function valid node, left, right checks whether the current node's value lies strictly between the allowed range defined by its ancestors left, the maximum value allowed from the left side, and right, the minimum value allowed from the right side. If the node is none, it is considered valid by definition. If the node's value violates the range node.val is less than or equal to left, or node.val is greater than or equal to right, the function immediately returns false. Otherwise, the function recursively checks the left subtree with an updated upper bound. The right is equal to node.val starting with -infinity, to infinity at the root, and at the root ensures every node is globally compared against all its ancestors, not just its parent, which correctly captures the true BST property. Time complexity of the solution is big of n, space complexity is big of h, and the patterns which are observed while solving this problem statement are range propagation, min-max constraint pattern. Second is DFS with state passing. Third is global versus local validation. Fourth is recursive invariance. Fifth is early termination. Sixth is implicit stack usage, space via height. Seventh is problem reframing. Instead of asking is this a BST, we can reframe it to is every node within its allowed range.